Okay, we're going to do that inquiry, the drawing inquiry to see if this helps anybody. So, and it's that I don't have a protractor, so I downloaded some polar paper to make the drawing on. It's a force table top, so it'll work really well. So here's the data that I gave you. There's three forces, how many newtons they are. That's force C. I don't know why it looks like a 6. And then here's the angles between all three of the forces. Point P is this point right here in the center. So we're going to do this to scale. We're going to do 1 centimeter equals 1 Newton. And I'm going to draw all three of these forces on this paper. So, and I could, so I'm going to do force PA. So point P to point A, vector A, is 3.9 Newtons. So that would be 3.9 centimeters. I'm going to do it right here along the 0 lines, good place to start. So there's 4 centimeters, there's 39 millimeters right there. And so that is, from there to there, is going to be PA. There's a vector. That's A. Okay. And then vector B is 4.6 newtons. And let's see. So the angle between A and P and B, APB, is 130 degrees. So there's 0. So I'm going to go all the way to 130 degrees, this line right here. And I'm going to come on here and I'm going to do 4.6. So basically 46 millimeters. I'll put that right on there. And go to there. So there, let's see, 10, 30, 45, 6. Okay, so there is vector B. Okay, and then the angle between A and B, or BP and C, is 125 degrees. So 125 plus 135 would be 255, which is right somewhere right here in the middle of this line right here. Okay, so I'm gonna come on there and let's see, how long is that one? 3.6 newtons. So I'm gonna put a 36 right there along that line. Something like right in there. Okay. There we go. So that's vector C. And then 0 all the way around here, it should be 105 is the left angle that I have. That should work. 105 plus 255 should be taken back to 360. Okay, so there's my 3 vectors. Okay, and I think I'll maybe mark them in a little bit better here so you can see them. Vector C, vector A, vector B. So there's our 3 forces on our force table. And then what the drawing instructions say is that we're gonna basically add A and B together. And so the way you can do that at the tail head method, I could take this vector B and I could put it on the head of this one, or I could take vector A and put it onto the head of this one. And I'm going to do actually both of them, and that'll make a parallelogram. And then I can get the diagonal of that parallelogram, which would be the resultant. So really, I need a better protractor here. It's kind of difficult, but I'm going to try to just eyeball this in here. I'm going to try to go straight over, and force A was 3.9. So I'm going to try to go straight over from there, 3.9. So if let's see, 40, where's 1, 2, 3, 4, there's the 39. Okay, so that should be like about the length of A. And then basically if I connect these 2 up, this should be probably parallel to the B one, or pretty close to it. So there's a parallelogram. So there's B and added on, there's A added on. And so what we're going to do there is I'm going to draw the diagonal of that. And the diagonal of that should be basically the resultant of A and B together. So I'm going to come right here, and I'm going to go to that point right there. Okay. Like that. And we're supposed to label that. That is going to be called C, we'll call it C prime. Okay. So this is angle P, or this is PC prime, which is the resultant of these two vectors. And I'm supposed to label what that is. So if I measure that, it is approximately, let's see, 10, 20, 30, 10, 20, 35, looks like 36. Looks like 3.6, 36 millimeters would be 3.6 newtons. Okay, now we're also supposed to measure the angle AP, this is P, APC1. Supposed to figure out what that angle is. And it looks like it's kind of going right down the middle of this. So I'd say 75. Looks like APC prime is 75 degrees. Okay, so that's the first part. So then what we're supposed to do is we're supposed to take, it says number 5 says finally extend the force line PC. So here's PC. Extend the force line PC beyond P, so over this way, a distance equal to PC, and label this segment PC2. So what we're going to do is we're going to take this vector, we're going to flip it over and basically see how it compares to this vector. Because if you understand what we're talking about with equilibrant, the resultant of these two forces, which is this, should be the equivalent of this force. So it should be equal and opposite to this force so that this whole thing's in equilibrium. So we're basically going to flip this over on top. And this was how long? This was 36, right? So actually it comes out perfect for what that was, the magnitude of that. But we'll see if it ends up on the same angle. So if I come here and I do a 36 on the other side, and basically I kind of line up with this, then this one came out, it basically came out about perfect. So I can sketch in there, and pretty much I'm right on that line. So angle A, and we'll call that PC2. So if it didn't come out perfect, you didn't do it exactly right, then this might be a little bit longer. And so you'd have a percent error between your PC and your PC2. My PC2 actually came out to be 3.6 centimeters also. And my angle APC2 was also 75 degrees. So this came out perfect. Percent error equals 0. So that's pretty easy math. But generally, if you flip this over, it was a little bit longer, or it was a little bit off, maybe skewed off, like maybe it came like this, then you have a different angle, and you do a percent error between those two things. But this one came out really, really nice. So the resultant of these two forces, which was this, was actually the equilibrant of this particular force. And that's what you're kind of supposed to show in this inquiry, and that could be your drawing that you have in your lab.